virtual introductions. Good afternoon, everyone. I'm Anthony, and now I'm a PhD student at the Department of Mechanical and Electromechanical Engineering, National University. Today, I'm happy to share our research. Developing deep learning potential for molecular dynamics simulation of aluminum, niobium, titanium, vanadium, zirconium, high entropy alloy, hydrogen storage materials. Let me outline what we are targeting. First, I will introduce the background and the motivation of our research. Then, I will explain the simulation method and the deep learning approach we use. After that, I will show the result and discuss the findings. Finally, I will share our future work. Let me start with the introduction. As you can see in this figure, there are many different methods for hydrogen storage, including high-pressure gas hydrogen storage, liquid hydrogen storage, and metal hydride, and something else. Each method has its advantages and challenges. Today, we focus on metal hydride, because metal hydride offers good safety and a good storage capacity. Metal hydride works through a simple process. Hydrogen gas particles first absorbed into metal crystal. In this process, heat is released. When we need hydrogen back, we apply heat, and the hydrogen atoms dissolve from metal hydride crystal. This process is reversible and provides a safe way to form hydrogens. This is the reason why we choose high entropy alloy. High entropy alloy has four effects and a very excellent for hydrogen storage. First is high entropy effect. Their disordered structure provides more hydrogen storage size, and a high melting point and stress makes structural stability during hydrogen storage. Second is lattice dispersion effect. Atomic size difference make lattice diffusion, increase gas and deflect. It make more void travel, enhance hydrogen atom diffusion and aggregation. Third is sluggish diffusion effect, which results in lower diffusion rate. Melting element composition, heater diffusion, and promotes nanostructure formation. Nanostructure enhance hydrogen absorption and dissolution kinetics. Fourth is cocktail. It makes unexpanded synergies. Tunable composition allows customizable hydrogen storage performance. This table and figure show why PCC structure is preferred for hydrogen storage. PCC structure has 8 octahedral sites and 12 tetrahedral sites per unit cell, which is more than FCC and HCP structure. The hydrogen to metal ratio is high for structure with a PCC arrangement. This makes PCC high entropy alloy very promising for hydrogen storage application. This theory table shows how elements are classified by hydride formation. The red elements are A-type elements that could easily form hydride. The blue elements are B-type elements that couldn't easily form hydride. By mixing different types of elements, we can control the hydrogen affinity of the alloy. So we can use it to design new hydrogen alloy for hydrogen storage. Based on the frequency of an analysis of PCC hydrogen alloy, we know titanium, polonium, niobium, and zirconium are the most used elements. And we add aluminum because aluminum can reduce density and maintain good hydrogen storage properties. So this gives us the aluminum, niobium, titanium, polonium, zirconium 5-element system in our research. Now, let me explain our simulation method. We need to balance accuracy and efficiency. Density functional theory, DFT, gives high accuracy but high computational cost. Molecular dynamics has high efficiency, but it depends on potential accuracy. Deep learning potential, DLP, provides good balance of accuracy and efficiency. This is the reason why we choose deep and liquid approach. Here are key steps in developing our deep learning potential. The workflow has 5 main stages. First is data preparation. We use quantum espresso, perform DFT calculations, and collect training data. Second is data conversion. We transfer the training data into deep and into file format. Third is model training. We use deep and liquid training model with neural network. Fourth is model validation. We test our model by comparing prediction with DFT calculations. Finally, we use them to run practice simulations to study material behaviors. We have developed several Perl and Python scripts to help with our research. These are homemade scripts created in our lab. For example, free-format graph contains script for QE calculation. PB training contains script for DLP training. Index for DLP contains script for length simulation. And all scripts are pushed on GitHub and accessible to other researchers. This table summarizes the DFT calculated structure for training data set. We collect 6 X structures from material projects, including unary, binary, and ternary composition. We also generate 877 structures with different composition and crystal type. In total, we have 945 structures covering various simulation conditions and temperatures. This all-around data set ensures our model can handle different conditions. Now let me present our result. This learning curve shows how our model improved human training. As you can see, the MSE for energy, force, and the virus stress all decrease steadily with the training step. The model conversion will, after about 400,000 steps, it means our training is successful and stable. This scatter graph shows the correlation between EFT and the DLP predictions for training set. The obscure values are very high. 0.995 for energy, 0.91 for force, and 0.96 for virus stress. The point graph tiling around the diagonal lines indicating excellent agreement between EFT and our model. More importantly, the validation results show similar accuracy. The obscure value remains high. This consistency between training and validation shows that our model is not overfitting and can generalize well to a new structure. We use steps to perform molecular dynamics simulation at 600 million. As you can see, the initial structure, after the initial structure was relaxed, it showed 99.1% ECC structure. And after 20,000 simulation steps, it still maintained 83.1% ECC structure. This means our model can correctly predict the structural stability of high entropy alloy at high temperatures. We also test our model by calculating mechanical properties. Compared with reference value, our model shows good accuracy for lattice constant with 0% error. And the C11, C12, C44, a less constant, show error within 10%. The gross margin, the shear margin, the Young's margin, shows error around 5 to 50%. It means our model can accurately predict the mechanical behavior of a high entropy alloy. We have successfully established a deep learning potential model for the aluminum, niobium, titanium, vanadium, zirconium, 5N alloy system. Next, we will continue to perform DFT calculations for high entropy alloy hydrides, expanding the hydride database for training. Our goal is to develop a complete DLP model for the aluminum, niobium, titanium, vanadium, zirconium, hydrogen 6-element high entropy alloy hydride system. This will enable us to calculate hydrogen storage capacity under different elemental conditions. I would like to acknowledge the support for the Ministry of Science and Technology of Taiwan and the National Tsinghua University. Their funding and the resource made this research possible. Thank you for listening. If you have any questions, I'm happy to answer.
Yes, thank you for your presentation. Can you tell us why did you choose the PT ensemble? How do you consider the change of volume to unit cell? volume of the alloy.
Mean why we should do MDK approach?
I mean, you want constant temperature and pressure, right? And what about the volume of the alloy that you're suggesting?
Because the DFT calculation is very expensive, so we just use maybe 32 patterns in the system and get some maybe NBT ensemble, get this structure, force, and viral to put them into the deep learning training process.
Yes.
So volume is not the main consideration in our study.
So after the DFT calculation, you're going to expand it to a larger structure using the molecular dynamics simulation, right?
Yeah.
So and there could be a significant change in volume for the alloy. So I'm trying to think in the practical aspect. So if the volume change is huge, then maybe you need to.
Oh yeah. For the deep learning potential, we use a much larger system, more than maybe several thousands patterns in our ND simulation.